even the stability and the stabilization properties of a simple pendulum system can be less obvious than we think, right? And this is the computation I mentioned yesterday that Lord Maxwell did. He took a harmonic oscillator, a pendulum, linearized one. He observed, right? We did it yesterday, just multiplying this equation by the velocity x prime, something that you also do in the context of partial differential equations when dealing with wave-like problems. He observed that the energy was conserved, what is completely compatible with the fact that solutions are simply, combinations of complex exponentials, right? Dealing or leading to a motion which is completely periodic and with constant amplitude. And then he said, okay, how do we stabilize the oscillation properties of the system? We can do it by adding this feedback term. So you see, this is a feedback, right? So this is a feedback or a damping term, right? We are damping, we are dissipating energy on one hand. On the other, we are doing it using a feedback mechanism. Why I do refer to the feedback? Well, because if you just call the right-hand side of this equation, you just call it, say, f of t, right? In the context of mechanics, f of t is the force applied to the pendulum, to the harmonic oscillator, right? So you have a pendulum which is oscillating, but you can also push it up and make the oscillations being, more accelerated, larger amplitude, or you can, when it's coming to me, you can push it backwards so that, these oscillations are damped, are dissipated, right? So here you see that this is a feedback mechanism. This is an important concept, as I mentioned yesterday in control theory, because what you do is actually that at every time instant, you measure the velocity x prime of t of the pendulum in oscillation, you measure the velocity, and then you apply a force which is proportional to the velocity x prime of t with a minus sign. So is going against the velocity. When the velocity is positive, I push with a negative force, and when the velocity is negative, I am pushing with a positive force. So I am always doing, I am pushing against the tendency of the motion to evolve, right? And I am doing it with say, multiplicative constant k, right? So in principle, our first intuition says, oh, if I do this, so I'm always pushing with a force which is proportional to the velocity, but with the opposite sign, the solutions will decay, right? The solutions will decay faster and faster whenever I increase the multiplicative constant k. Because larger constant k, it means that larger is the force I apply, right? This was, this is the first intuition. In fact, I think I didn't say yesterday, the fact that this term here is a damping term, you can see it very nicely by doing the same thing, right? So if here what we did in order to get the energy conservation was simply multiply the equation by x prime of t, right? And observe that this equation leads to the conservation of energy d et dt equals 0. Here, if you do the same, then you get a dissipation law saying that the derivative of the energy is minus k times x prime t squared. So you see indeed that by adding this dissipative term, in principle, we are dissipating energy, okay? And according to this very simple law, one could think, well, and indeed, not only I'm dissipating energy, but the bigger is the K, the more I am dissipating, and therefore the faster the decay rate will be. As we said yesterday, in order to analyze the decay rates of a linear differential equation, it is sufficient to look to the roots of the characteristic polynomial on the complex plane. For in the absence of dissipation, the two roots are purely imaginary, and the solution is a pure oscillation. When you increase the dissipation a little bit, the roots move to the left, losing a little bit of imaginary part. But then, as we mentioned yesterday, when you reach the critical value k equal 2, right, where the spectral abscissa is -1, the two roots collapse. And after that, right, and after that, things get worse and worse because one root comes to the left and the other one comes to the right, right? So you see that already in this simple example that you can compute explicitly, and this is what Maxwell did, you can see that, you know, the control properties, in this case, control simply means how fast, right? As I have drawn yesterday, right? So we simply draw how fast as a function of the damping K, damping constant K, how fast, right? The energy decays, you realize that this is nothing, this is not really a monotonous function. For small amplitudes of K, this is indeed a monotonic function. But when you get to K, which is critical, right? So K equal 2, then the decay rate starts decaying, and then the more you do, the more you dump, the less results you get, right? And this level of decay is precisely 1, right? So you cannot achieve with this simple mechanism faster decay rates that that the one associated with K equal 2, which is the decay rate K equal 1. At this point, I wanted to propose you an exercise. This is the exercise. You can consider a more general system of the form, where now, rather than considering simply the harmonic oscillator with damping, you also allow for a second term, right? Depending on the position itself. So this is a new feedback mechanism, right? Sorry. This is a new feedback mechanism, right? X double prime plus X equal to minus K X prime minus PX. But this is somehow a more sophisticated feedback mechanism, which is using both the position of the pendulum X and the velocity of the pendulum X prime in order to determine which force you are applying through this feedback law, right? And so here, of course, because you have two terms, the constants K and P can be chosen arbitrarily, right? And then the exercise consists in showing that if, rather than considering this simple velocity feedback, you allow for more sophisticated feedbacks that are able to combine both position and velocity, then you can achieve the decay rate you wish without any limitation. Okay, so we see here already some of the key ingredients in control theory, right? So you see that, in fact, whether a system can be stabilized, so this could be said that this is a problem of stabilization. Why? Because, you know, for the original system, in the absence of damping, the solutions were purely oscillatory without any decay. And through the addition of the damping, we have achieved to guarantee that they converge to 0. Okay, so this is a problem of stabilization. So this is a control property in infinite time, right? So we say that the system is controlled in infinite time because the solution is, the amplitude of the solution and the amplitude of the velocity, which is just equivalent to the square root of the energy, is decaying exponentially. So this is an exponential stabilization property that can be interpreted as a control property in infinite time, right? Because I only achieve the zero equilibrium when t is equal to infinity. Of course, zero is an equilibrium, right? So x equals 0 is an equilibrium. And actually, in this case, is the only equilibrium of the system, right? Because if you tell me what are the solutions x equal constant, when does the constant x equal z verify this harmonic oscillator? Where there is only one. The only one possible is z equals 0. Why? Because when you compute the derivative of x, if x is a constant, the derivative is 0, the second derivative is 0, so the second derivative is 0. So in order to guarantee that x double prime plus x equals 0, you need z to be equal 0. So 0 is the only equilibrium of the system. And what we have shown is that through this damping mechanism, the simplest damping mechanism in which you simply drag energy, remove, take out energy of the system proportionally to the velocity, you achieve an exponential decay and exponential stabilization property. Of course, someone could tell you, well, but you never get to 0 in finite time. This is true. So far, with this figured mechanism, we don't get to 0 in finite time. We need an infinite time to get to 0. But of course, in practical applications, you are not that much interested on getting exactly to 0. Maybe you are just interested on getting, the amplitude to be less or smaller than epsilon. I mean, if you are working in a company, 0 doesn't exist. I mean, your boss will tell you, well, we need x to be below 10 to the power minus 3. And then, of course, this is something you can achieve, right? Because if you tell me that you really need, x to be less than a given epsilon, I will tell you, well, I will use simply this formula here, and I will say, well, I take t, right? I take t such that c exponential minus alpha t is less than epsilon. And this is something that I can always do by choosing properly the t. Why? Because then I need exponential minus alpha t less than epsilon over c. This is minus alpha t less than the log of epsilon minus c. And this is just the same as saying that t is greater than the absolute value of the log of epsilon over c divided by alpha. Okay, so you can always prove with such an exponential stabilization property, asymptotic stabilization property, you can always show that you have nearly achieved the equilibrium x equals 0 in a finite time, provided the time is long enough depending on epsilon, right? In some sense, this is not an exact control property because we don't get really to the equilibrium x equal, say, 0, right? But we get there in an approximate manner. So this is exact control versus approximate control, okay? So, but you see that in order to realize such a simple, you have to really implement that in practice. I mean, from an ODE perspective, from the perspective of the analysis of ordinary differential equations, I mean, this is very cheap. You can just draw here the damping mechanism you want and just then compute the eigenvalues of the corresponding characteristic polynomial. But if you are, really dealing with this system in a practical manner, in a laboratory, what do you need? So you need two things, right? You need two devices. Of course, you need a device that is able to apply to the system the force you like, right? So first, I will need an actuator an actuator which is designed to implement in this feedback, in this harmonic oscillator. I need an actuator that is able to apply a force which is proportional to the velocity, and with a constant that you can regulate. You can choose the K, right? So this is the same exactly as in the, as in the air conditioning system, where you can not only regulate the temperature, you say 19 degrees. So this is your asymptotic equilibrium you want to achieve, 19 degrees. But not only this, you also have a second, say, button in which you can choose, right, the intensity of the flux of air. You can put it milder, or you can make it stronger, right? So then you are regulating, the constant K. Not only you are choosing the target, 0 in our case, but you are also choosing the intensity in which the device is working. Of course, the bigger is the intensity, in principle, the faster, the cooling process will be, okay? And now, so in order to be able to apply this feedback law, therefore you need an actuator, a device that is able to, at any time, in a feedback manner, right, apply a force which is proportional to the velocity first. But then I ask you, okay, so even if you have the actuator, how is the actuator gonna choose the force to be applied? Well, you will tell me, well, you simply need, Enrique, to take Ft to be minus K x prime t. Yes, but then you see that you realize that you need a second device, the sensor, because you need also a patch attached to the, or a laser, measurement device, some kind of camera, watching, the pendulum oscillating. You need it in order to be able to measure the velocity, and then, right, out of this measurement that the sensor is capturing, indicate the actuator, right, to apply a force which is proportional to the velocity, right, with proportionality constant K that you can choose. Okay, so you see that here we need sensor to measure x prime of t, and we need an actuator to apply the force minus K x prime t. Right? And what I'm saying in the exercise is that if, rather than applying this feedback mechanism, K x prime, you apply a more sophisticated mechanism, which is K x prime minus Px. If you do it with combining position and velocity, then you will get an arbitrarily fast decay rate. So your, cooling device will be more efficient if you are able to combine both, right, the K and the P. You will tell me, well, but in order to do this, I need one more device. I have the device, I have the actuating device. Because I have the actuating device, fine, I can regulate F to be not only minus K x prime, I can make it to be, minus K x prime t minus P x t. But I need one extra device, right, in order to do that. Could you please tell me in the chat what is the extra device I will need in order to be able to do this implementation? So far I said one sensor device to measure the velocity x prime, and one actuating device to really inject into the system back the force F given by the formula. But now I need a third device, right? The third device I need is a second sensor, which is able to measure the position itself, right? So then you will need position, and then velocity, right? in order to be able two sensors, one for the position and one for the velocity, and then finally one sensor in order to apply the force, right? So you see that in control theory, in practical applications, is not only about doing mathematics, but you also need to take care of the fact that, you know the position and the velocity, right? And very often in practical applications, we don't have that information, right? So, for instance, when a friend of yours by WeChat tells you where the person is, right? So you want to meet, and then you ask him where you are. Well, the address is very complicated. I don't know. Okay, I send you I think you can do it by WeChat, right? So yes, so there is here one option is, okay, I send you my position. I'm sending my position to Professor G. Lin, right? So if he wants to meet me here in Basque Country, in the north of Spain, which is like 10,000 kilometers away from Changchun, he knows where I am. So he has my position now, okay? But he doesn't see what is my velocity. He doesn't know whether I am standing or whether I am moving in my apartment, okay? So then this will be a second device. More precisely, he will need, right? Of course, if you are able to send positions, sequentially, one instant of time after another, then you can also extrapolate what the velocity is. But if I send you my position just once, you will never know. You will never know whether I am sitting in my office or whether I was passing by with my bicycle, and maybe by now I am 500 meters away. Okay? So you need sensors, right? You need information about the system, and then you need actuators. You need devices in order to act efficiently on the system. Okay, so this was a short introduction to control. Now, as I said yesterday, oftentimes when, as an applied mathematician, you are faced to control a system, there are different paradigms you can use, right? Sometimes, the paradigms are more those of active control, as in the control of the pendulum here with the computation of Lord Maxwell back in 1868, 150 years ago now, right? So this computation goes back 150 years. It's a long time, but it's not that much, as I said yesterday. So please think that Aristotle was already claiming the need of developing automatic control, right, 2,500 years back. And that this computation about the stability of the pendulum was run 150 years before, right? So it took a long time before, this computation was done. Now for us, it's a very elementary computation, but at the time it was striking. Okay, by the way, I should say that here, when I'm dealing with the system x double prime plus x is equal to 0, is also very important from a mathematical perspective or a control perspective to really say, what is the real state of the system? What are the unknowns of the system? What do I need to know in order to really, understand what the position of the pendulum is? As I told you before, I have sent my position, right, to Professor Kai-san, but I didn't send him my velocity, right? So, he doesn't have complete information about myself. So if you really want to have full information on the system, you have to think on what is really the state of the system. So you see, this is something that was already answered by Cauchy, right? So Cauchy, French professor, more or less the same time as Lord Maxwell was doing these computations probably in the UK. I think he was born in Edinburgh. He was probably working in the university there, or maybe in London. Cauchy was the person who thought on a more systematic way of dealing with differential equations. So it was Cauchy, who said, well, you should stop trying to solve explicitly differential equations. You will do it in some cases, and this is the simplest example in which, you can find the solutions of the ODE by simply solving the characteristic polynomial. There are many other examples where you have changes of variables, you have Floquet theory for periodic equations, you have Riccati differential equations, you have Hermite differential equations, you have several examples of differential equations that are more or less tricky, but that you can solve in an explicit closed manner. But Cauchy said, in general, you will never be able to find the explicit form of the solution. Why? Because after all, solving a differential equation is like computing the primitive of a function. And as we know, even though in class, when we are in the bachelor diploma, we learn how to compute the primitive of basic functions like trigonometric functions, polynomials, and then we use special tricks to solve, for instance, exponential functions, the integration by parts, changes of variables, rational functions, and so on. We know that in most cases, we will never be able to give a closed form for, the primitive of a complicated function. We know that primitive exists. As soon as the function is Riemann or Lebesgue integrable, you can define the primitive. You can say how regular it is. You can even give the asymptotic values when, t goes to 0, the length of the integration interval goes to 0 or goes to infinity, and so on. But if you ask me, can you give a closed formula? In general, you will never be able to do it. So Cauchy said, for the same reason, when you are solving differential equations, you will, in general, not be able to give a complete solution, explicit complete solution. So he said the best you can do is to formulate in a rigorous mathematical way what your goal is. And what is our goal? Well, our goal is to give an initial data for this system, giving me information on the system at t equals 0, try to determine what the future evolution of the system will be. This is the same as what we look, right? When we go to, the weather application, right? In the portable phone, and then we say, oh, I'm where I am here in Basque Country now. Today the temperature is going to be 27 degrees, summer temperature, but tomorrow it will go down to 19. So there will be a substantial drop on temperature, 8 degrees, right, minus tomorrow. Okay, so not only I have the initial datum now, but I can also determine the future evolution of the system. And then here, because this is a second order system, we know that in order to determine what the future evolution of the system will be, I need both the position and the velocity. Why do I need position and velocity? Well, because actually the way to understand second order in time differential equations, right, is to write it down as a system of first order equations. So the system will be x prime equal y. So I introduce an auxiliary variable y, and then I say that y prime, because y prime is the derivative of x prime, this is going to be x double prime, this is equal to minus x. So I can write, if I now define a vector xy for the state, the differential equation becomes z prime equal az, where A is the anti-adjoint matrix, right? 0, 1, minus 1, 0, right? And this is actually what is telling me this Cauchy way of writing the second order differential equation as a first order system. This is the one that tells me, you see, actually, the state of this system is not only the position, but it's also the position plus the velocity x prime. Okay, this is the full state of the system. Okay, so you want to really understand where you stand about, you know, the oscillations of this pendulum, you need to know both x and x prime. But of course, in order to measure each of them, you will need, right, two different sensors, or at least if you want to extrapolate, right, as I said before, if you want to extrapolate x prime out of x, you will need the measurement of the position through the sensor that is giving you the position, but you will need it in several time instances, right? Because then I can do it. I can, you know, you give me what is xt, and then you ask me, can you determine out of xt, can you determine the velocity? Well, the answer is not. But if you give me x at time t1 and x at a different time t2, which is close to t1, so t2 being, say, t1 plus a small increment delta, then I can guess what the velocity of x prime is going to be. This is going to be by finite differences, x at time t2 minus x at time t1 divided by delta, okay? But you see, all these issues matter in control theory. It's not only about doing mathematical analysis, but then it's about implementation. And for the implementation of these control mechanisms, you need both sensors and actuators. Okay, but this was a very, very dynamical perspective. This was in the context of noise reduction. You remember yesterday I said, this is where you find the two, say, main paradigms of control theory. The active paradigm, active control, is very much about dynamical systems because you are measuring noise again and again and again. And according to the measurement of the noise in real time, you are applying an anti-noise in order to, you know, diminish the noise. This is exactly what we were doing in the harmonic oscillator, right? Right? We were taking the harmonic oscillator. We're taking the harmonic oscillator, and we were, you know, in real time applying this feedback, right? Which requires the measurement, right, of the through the sensors and the actuations through, this will be the anti-noise. We said this is the very dynamical perspective to control problems, but there is another one which works also pretty well in many circumstances, which is the, you know, producing once forever an intelligent design, right? If we design the home carefully, then this home will be very well isolated, and maybe I will not need to invest my energy and money on buying sensors and buying actuators because it was, you know, designed correctly once forever when it was built. And this is the perspective rather of the calculus of variations, right? Okay, so this is the perspective of the calculus of variation. What is the calculus of variations? Well, in principle, calculus of variation, you see what it means, right? It means computing, calculating variations. It's exactly what I did before, right? So you give me a function, right, x of t, and then I say that x prime of t is more or less xt plus delta minus xt divided by delta, right? I maybe, you know, at that time, again, you know, that, you know, the concept of derivative was, you know, cued by people like, you know, Leibniz, Newton, but it was more intuitive. Actually, nowadays, in order to say what the derivative of a function is, we know exactly what it is. We know that the derivative is the limit, and is the limit of this incremental quotient as delta goes to 0. And we know exactly what the limit means because we claim that, you know, the limit of a function is a given number provided for every epsilon there exists a delta and blah, blah, blah. But, you know, all these rigorous definition of limit, again, was given by Cauchy. It came much after people were manipulating, you know, the concept of derivative, okay? But we understand, you know, the derivative as being the slope you know, is being the velocity, is being the increment, is a variation, right? This is what the calculus of variations is about. So you compute variations, and then because you are computing the variations, right, you can really say, oh, this configuration looks better than the other one. It's like, you know, when in your telephone you are, you know, you type messages and then you can choose, for instance, the size of the characters, or you can choose the brightness of the, right, of the screen. So during daytime, maybe you will choose a very bright screen, but then in the night, I mean, this too much brightness will hurt your eyes, right? So you will regulate brightness up and down, okay? So this is the calculus of variation. And then a very typical example, you know, is this isoperimetric inequality, right? What does the isoperimetric inequality say? So this is the, I will go back to this, the isoperimetric inequality. It says the following. This is a very simple example, right? You have functions of one variable, one real variable. The functions are defined in the interval a, b, you know, functions, you know, y is a function f depending on x. This is the x-axis and this is the y-axis. Okay. I'm considering all possible functions defined in the interval a, b. I know that when I draw the graph of this function, I will simply find a curve, right? Okay. And now I ask you, okay, so you see here two functions, right? So one is here. This is a circle, right? So this is the arc of a disk of a circle. And then this is a more oscillatory function. So what the isoperimetric inequality says is that in between these two functions, there is one that is better than the other, right? Why? So the circle, you know, is better than this more oscillatory function. Why? Because you see, these two functions produce the same area. So the area generated by the circle, right, is this purple area here plus this blue area here, right? Why? Because this is the area below the graph of the function. In the case of this more oscillatory function, you know, the drawing was done in a deliberate manner. The area is the same. You say, you see, the area is the same. Why? Because here, you know, when I consider this more oscillatory function and I look the area below, the one I will get out of the integral, right? So I am just computing, saying that the area is the integral from a to b of fx dx, right? So the area below is going to be the same, because what I'm losing here with the blue region that is now above the graph and therefore is not counted on the integral, what I'm losing in the blue, I'm earning it, I'm gaining it on the red. So the area is the same. So you see, the two functions are equally efficient. And I will tell you, no, they are not equally efficient because the area is the same. So we have F1 and F2, and the area they generate is the same, right? But the length of this arc, because of these unnecessary oscillations, is much bigger than the length of the circle, right? So the length of F2, the length of F2 is greater than the length of F1, and in that sense, you know, F1 is better than F2, right? Why? Because I was able, you know, to generate the same area with length, with perimeter, which is smaller, right? Okay, so it was actually Leonhard Euler who, you know, thinking on these concepts of optimality and the calculus of variations, right? He said that, you know, since the fabric of the universe is most perfect and the work of a most wise creator, nothing at all takes place in the universe in which some rule of the maximum or the minimum does not appear. So basically, with different words, he was saying that in most processes and phenomena of nature, nature is choosing always configurations that are optimal, right? So for instance, for humans, we have designed the chairs so to be sitting in a comfortable manner, right? We avoid falling on the floor, right, due to gravity. So we compensate gravity, and this allows us to keep a position that allows us to, to talk to our camera and communicate with people in an efficient manner while I am writing. So we have chosen an optimal configuration. So this is what Euler said about the rule of the maximum and the minimum, okay? And the example I was giving you before is precisely the one of the isoperimetric inequality, right? So the isoperimetric inequality says that if you take curves, closed curves of a given length, L, and your goal is to maximize the area, right? Then the best possible configuration is the circle, right? So if you do a disk, right, you can guarantee it is optimal. Anyone else that with the same perimeter will choose other shapes like this one, which is more elongated, so eventually the perimeter is the same, but the shape is thinner and longer, right? You can guarantee, listen, your drawing is worse than mine. Mine contains more area, right? And this is something that is known. I mean, there are, this city, Carthage in the north of Tunisia, or the city of Köln in Germany. I'm sure cities in China are also more or less designed that way, right? They often adopted the shape of a circle, or in this case, a demi-circle, a half circle, because a river is passing by. The town is to one side of the river. And when you look to the perimeter of the town, you see how this is exactly a half circle, right? Why? Well, because adopting a circle or the arc of a circle, you know that you are maximizing the area. So you are maximizing the urban area where people need to live, right? And the more area you have, the more space you have, the more comfortable your life will be. But on the other hand, right, you maximize the area by keeping the perimeter minimal, right? And keeping the perimeter minimal is important, in particular when when you are in a conflict situation and you have to defend, right, protect the town and the inhabitants of the town from the possible attack of outsiders. Right? This is the isoperimetric inequality. And this is a very simple concept. Now, you realize immediately that, I mean, this simple concept that we, as I mentioned yesterday, this was the Arpenodaptai in the ancient Egypt. Their job was to simply draw straight lines. This looks very simple. Well, it looks simple, but if I have to draw straight lines that are longer and longer and longer, I know I'm having more and more and more difficulties, right? Okay, so now, if rather than telling you, you have to compute the shortest distance on a plane where I know it's always a straight line, I have to do it on a complicated surface like this one. I tell you, this is the point A, and the point B is here. Then I ask you, what is the shortest distance? What is the geodesic arc? What is the curve living on this surface on which you are walking, right? So you are this walker here. What is the shortest distance from A to B? Then, well, maybe you will have more difficulty. So I guess it will be something maybe like that, right? But maybe some others will say, no, I would just do this and then this, and some others will say, well, I maybe I take it a bit longer from here and then I do this. So you see in those cases already that computing what the geodesic is can be not so obvious. So even concepts that are trivial apparently and that are easy to formulate and solve mathematically in simple configurations, like for instance in the flat space, as soon as you get into some complicated manifold, things might get much more difficult. And then you need tools, right? And in particular, the calculus of variation is doing this. So the calculus of variation has also a long history. There is a beautiful book that I recommend you all, right? So it's this book by Ernest Heider and Warner. Heider is the father of the recent Fields medalist, Heider, on stochastic partial differential equations. And this book is a Springer book, undergraduate text in mathematics, maybe was published, I don't know, 15 or 20 years back. Okay, and the title is the book is Analysis by Its History. It's a very interesting book, right? So what they say is, okay, so we don't present calculus as we normally do in class, right? So if we are teaching an calculus or analysis course, I'm sure is the same, you know, in Jilin University, right? If we present a calculus course, we will do it in the, you know, in the order which is the most conventional one, in which I will say first, I will introduce the notion of limit. Okay, I will say what the limit of a sequence or the limit of a function is. Out of the concept of limit, I will introduce the concept of continuity, because I will say that a function is continuous whenever, right, the limit coincides with the value of the function. Once I have the concept of continuity, I will introduce the concept of derivative, and I will say, well, the derivative you see is given a function which is continuous. Then you can build the, you know, the incremental ratio, and then you will check the limit of this incremental ratio. And if you have a limit, then you will say this is the derivative, and you will say that the function is differentiable whenever the derivative exists, and so on. Okay. You can then define higher order derivatives and so on. And then in the end, you will be able to define the integral as being the reverse operation to the derivation. And then you will have the concept of primitive, of, you know, indefinite and definite integrals, areas, applications, volumes, and all this. Now, when you look to how the history of calculus was, you realize historically it was completely the opposite. As I said before, you know, the concept of limit of epsilon delta came much after, you know, people were manipulating, you know, derivatives and differential equations, right? So everyone understands that this is a continuous function versus this one that is not continuous. People didn't need, for centuries, didn't need the concept of rigorous concept of, say, limit in order to manipulate these objects and realize that, of course, these are completely different dynamics. This is a smooth dynamics. This is a jumping dynamics. Everyone understands that, okay? So then in this book, what they say, we will explain analysis again, but we will do it from an historical perspective. And then the book is full of very interesting examples. This is one of them. This is the Snell law for the refraction of light, right? The Snellius law. Snellius, you know, he already knew this law, right? He knew that, you know, if the velocity of propagation of light in this medium is v1 in the upper half, right? Like in here. So air and water, for instance. So this could be air. This could be air and water here, right? If the velocity of propagation of light here is v1, well, light or anyone, it could also be a pedestrian that is running, right? And so here you are running in on the green, for instance, but here you are getting into the sand. And then you know your performance when you are running in the green or in the sand is not the same. There is much more friction, there is much more fatigue on the sand than on the green, right? So green and sand, right? So this is also because, you know, in the tennis championships, you distinguish Wimbledon and Roland Garros because the surface on which, you know, the tennis players are playing is not the same. And because of this, you know, the performance of every player changes, the strategies have to change, the energy you need is different, the velocity of the ball is changes also, and therefore some surfaces need different, say, qualities from players, okay? So then Snell said, listen, when you move from a medium in which the velocity is V1 to velocity V2, what the light does is that in case the angle of incidence of light here is θ1, and you measure this angle of, you know, incoming light, the angle of the incoming light to the interface. This is the interface because this is the equator, this is the border, the line on which you are moving from one medium, air, to the other, water. Okay, so this is what we call the interface. Interface in any kind of application of mechanics refers to this line, this surface, which is separating one material, one medium from the other, right? So in heterogeneous media, if the medium is homogeneous, you know, everything is the same. Whenever you are, you know, gluing two different media, two different materials, then you are doing it along an interface, okay? So this is what the interface is. And then what Snell said, if the incidence angle, if the angle θ1 along which, you know, the ray of light is getting to the interface is given by θ1, right? And how do I measure θ1? Well, in order to make it without any ambiguity, what I do is I have the interface, I have the normal, the perpendicular vector, and then I measure the angle θ1, right, along which the light is incoming. Then he said, if the angle of the incoming ray is θ1, the outgoing angle, right, after refraction, it will be θ2, right? And the relation θ1 and θ2 is given by, you know, these formulas, right? So the sine of θ1 divided by the sine of θ2 is V1 divided by V2. Okay, so then, you know, Pierre Fermat, who, you know, he is very celebrated because he tuned, you know, the celebrated Fermat theorem. Actually, for him, it was a conjecture, right? Because he said that, you know, these equations, you know, they don't have solutions for integer numbers greater than 2, right? 3 or more, right? And it took like 350 years for the mathematical community to prove it. This was done eventually, you know, like in 1992 or so in the 90s by Wild. So Fermat, the same Fermat that said that he had a proof for this Fermat theorem, but that he was not writing it, right? Because he didn't have enough space in his book for the proof, right? The same Fermat that thought had a proof of this, but very probably he didn't, because it took 350 years to the mathematical community to develop the theory enabling the proof of that statement, right? The same Fermat said, oh, you know, if this Snell formula is correct, it is certainly because the light, according to this principle of Euler, that in nature all processes try to be optimal, try to minimize or maximize some performance. What you know, Fermat thought is that when you are dealing with the propagation of light, certainly the principle that the light is applying in order to move from P to Q along this broken line, and this is the the visual, impact that this has, right? We see that a straight stick, which is, this is a pencil, which is on a glass of water. We see how it is, curved, like broken there. We know it's not broken, it's just an optical effect. He said that if the light is following this capricious broken line, is because the light is trying to minimize the time needed to travel from P to Q. And he said, and I will try to prove this. And then you see, nowadays, this is a very simple calculus exercise. This is explained in this book by Harrer and Warner. You can do it in the following way. You say, okay, this is the point A, and this is the point B. I change notation a little bit. This is the angle alpha 1, and this is the angle alpha 2, right? Then I have the length in this horizontal line. The horizontal distance between A and B is L. The height of capital A, of the point capital A, is small a. The height of the point capital B in the southern, in the lower hemisphere, is small b. Okay? And then I am given the velocity v1 in this medium for the propagation of light, and the velocity v2 in this medium for the propagation of light. So what is the problem here? The problem is to determine x. So what is the point x? So I can just say what the point x is according to the distance from this crossing point to the, to the left extreme. So x will definitely be between 0 and L. So if I will choose x to be 0, then the line will be something like this. So this is certainly not very good, because we see that the distance is, very long. Or we could take it x equal L, and then this will be something like this. Probably not very good either. So the x will be somewhere in between 0 and L. And I have to choose this x so that the travel time of light is minimized. But what is the travel time? So the travel time of light from A to B, according to this broken line, is going to be the travel time in the upper medium plus the travel time in the southern medium. What is the travel time in the upper medium? Well, is the, the time needed to go from A to this crossing point is going to be the length of this hypotenusa divided by the velocity. But what is the length of this hypotenusa? Well, this is simply, according to the Pythagorean theorem, this is the square root of a squared plus x squared divided by the velocity v1. And then the travel time in the southern hemisphere, it will be the length of this hypotenusa divided by the velocity v2. And what is the length of this hypotenusa? Is the length of this arc, according to the Pythagorean theorem, is going to be the square root of b squared plus L minus x squared divided by v2. And then, Fermat got to this point. And then the question was, minimize the function t of x. So nowadays, this is a calculus 1 exercise. It is sufficient to compute the derivative of t and check what is the point x for which the derivative is equal to 0. But he didn't get it. And then he wrote to Leibniz. And he said, well, because Fermat was not able to solve the problem, he said to Leibniz, okay, so maybe you can try yourself, right? And then in the letter to Leibniz, Fermat, who was quite arrogant, he didn't say, I cannot do it, right? What Fermat said in his letter to Leibniz was that I admit that this problem is not one of the easiest, right? And this is something I always say to the students. I mean, now the next time you go to an exam with a professor, and then the professor asks you a question which is too difficult for you, or it belongs to a chapter that you didn't study, if this is a question you cannot really answer, a very elegant way of saying that to the professor is to say, well, professor, this question is not one of the easiest, right? So this is more elegant than saying, oh, I don't have any idea, or saying, oh, I'm sorry, I didn't study this chapter. You can always say, like Fermat, this question is not one of the easiest, okay? So Leibniz solved the problem. So you see, this was back in 1684, much before the works of Cauchy. So at that time, the concept of derivative was not clear. There was not a clear definition of what the limit was. So you didn't have the concept of the limit, and therefore people didn't know what a continuous function was. They didn't know what a differentiable function was. Despite of this, people were trying to solve this challenging problem from physics. And then Leibniz did it, and then he did it the way we will do it today. So you say, okay, I can compute the derivative of this function. And then when I make this to be 0, I see that actually, you know, the angle, right, the incidence and the outside angle are related by, you know, this is Snell law. And, you know, not only this is a critical point, but actually if you will take the second derivative, you will see that this is positive, and therefore you are guaranteed that this is the minimum and not the maximum, right? You see, this calculus 1 exercise in the end of the 17th century was too difficult for people like, you know, Fermat, and only Leibniz was able to do it, okay? Good. So 100 century later, the French mathematician Gaspard Monge, right, is who wrote this beautiful paper in French is sur la théorie de Debré et de Ramblay. I don't know how you translate this to English, but you know, he introduced what is called today optimal transport theory. Okay, so of course he was not the first one to do this in some sense, right? So the Arpenodaptai that were drawing, you know, the straight lines in the desert in Egypt, right? The, you know, the straight lines in order to help, you know, on the constructions of the giant pyramids, they were already dealing with these problems of optimal transport, right? But he was, you know, Gaspard Monge was really the one who really introduced the problem from a more mathematical perspective. The question being, again, a problem of optimizing something. So here, as we have seen in the problem of the refraction of light, Euler was right. Nature has chosen, you know, to propagate light in order to minimize the arrival time, right? So this is like when you book, you know, your train, you know, your fast train, you say, oh, let me book the train, and I check the possible paths. Okay, I will do it in a way that, you know, the travel time is minimized. Nature did the same with the light. Okay, and then here, right, Monge said, we should do the same. For instance, when we are dealing with civil constructions, right, we will be led to, you know, massive amounts of, you know, leftover material, and we will need to carry this to, you know, to some reservoirs, right? And we should place all this material, which is located in here, to this place, which probably doesn't have the optimal shape. And I would like to do this transport from this initial configuration to the last one. So in a way that, you know, we optimize something. So what do we optimize? Well, we have to check, right? But for instance, you know that when you are moving, I mean, as a student, probably you move from, you know, your hometown, your apartment with your family, your parents, you move to, you know, to the campus, right, in Jilin University, right? And then you have to take your belongings, your computer, your clothes, your books, your, you know, other, you know, sport devices, music, whatever, okay, food, right? Then when you have to move, you can do it in several manners. You could take the bicycle and then, you know, say, well, every time I take my bicycle, I can maybe transport one bag or 20 kilos. I do 20 kilos and then I go back and then I take the bag again, right? So 20 kilos. But if you have many goods to transport, if you have furniture in a home, it will take you a long time. It will be not very optimal. You will have to do many trips. And sometimes it will even be impossible because, you know, there are, you know, you cannot transport a big TV on a bicycle, for instance, right? So rather than doing it with a bicycle in many, many iterations, you could also take a car. I mean, you ask, you know, some friend to help you take a car. And then with a car, you can maybe in just one trip do the same as you can do with a bicycle in 20 trips. So this is much better, right? But again, if you are transporting a big apartment moving from one big apartment to another, and you have a lot of furniture of transport, again, maybe a car will not be sufficient. So you better then rent a truck, right? Because then you rent a van or a truck, and then in just one trip, you will be able to transport maybe what you can put in your car or 20 times, or in your bicycle 400 times. So with just one trip, you will be able to transport all goods from your home to the new apartment, right? In just one trip, something that with a car will take you 20 trips, or in a bicycle 400 trips. Okay, so this is optimal transport. So how do I move goods from one place to another, you know, optimally? At that time, right, Gaspard Monge, sur la théorie de Deblay et de Ramblay, he was really thinking on materials. He was thinking on civil constructions, the materials that you need, you know, stones, rocks, sand, the materials you need in order to build a house, right? Or any, you know, building a road or a bridge, right? So he was thinking on this. Nowadays, right, the theory of optimal transport is called of Monge and Kantorovich, because the Russian mathematician Kantorovich was the one who later, right, said, listen, right, the same way we transport, right, sand from one place to another, because I'm just building a new house, right? You can think when you are planning the economy of a country. I mean, this was, you know, these were intellectual, you know, very high-level scientists that were helping the Soviet Union to develop, you know, the economy of the communist regime, right? So you can think on how do you plan the economy in a way that the wealth of a country is better distributed among the different citizens. So you see that in that case, you are not thinking of transporting, you know, goods from one apartment to another, or you are not thinking on transporting sand from one place to another because you are, you know, you are facing some new construction. It was more about transporting, you know, some more untouchable, right, untouchable goods like economic wealth. You could think also on transporting culture, for instance, right? How do you do in order to, you know, diffuse culture in a country, or diffuse good health habits, or diffuse some other ethical values, okay? So then the theory that Gaspard Monge developed on very concrete applications to civil engineering was, say, upgraded, was extrapolated, was promoted to a higher level of abstraction that now can be applied in any possible field, right? This is the theory of optimal transport that people, of course, have also addressed from the perspective of partial differential equations. Why? Well, because, I mean, it's very simple. I mean, when you look to the theory of partial differential equations, the first PD you learn, right, is this first order hyperbolic equation that we call the transport equation, right, in which you know that the solution fxt is simply the initial datum f0 x minus t, which is simply taking the initial shape of the inertial datum and is transporting it to the right with a constant velocity equal to 1 without any deformation. So you see, of course, that the theory of optimal transport, right, as indicated here, right, is not only a theory of optimality, but is, of course, very much related, intimately related to the theory of partial differential equation. Then, according to Euler, there is a lot of calculus of variation in nature. So how this was done? Well, we don't know, right? So people like Euler or Newton, they address this issue by saying, oh, we are Christians, so we believe that there is a God, and certainly this God created the universe in a perfect manner, and therefore God knew the calculus of variation, and God did it according to the principles of minimality, right? But it's true that, in practice, very often in nature, you find these minimal surfaces, for instance, which are, again, related to principles often of optimality, in the sense that you are minimizing the area, you are minimizing the curvature, you are minimizing tension, right? This is also extremely, frequent in geometry and in the manifestations of the shapes of nature, okay? Now, calculus of variation and optimal control and control theory are very, very much related. So not only they are related because oftentimes when you formulate a problem, right, like, here in the problem of Fermat, right, when you formulate a problem, right, you say, is this a static problem? Is this a static problem? Or is this a kind of dynamical problem? Well, it depends. It's actually both, right? In some sense, it's a static problem. We simply say we minimize length. Okay, so we minimize simply the length, the travel time. So if I tell you I minimize the travel time, it looks that I am minimizing, right? I'm simply minimizing a function t depending on x, capital T depending on x. So it doesn't look like there is motion on it. But on the other hand, if I really think on what the light is doing, you see that this is really like a driver, right? That is driving in a motorcycle, and that eventually, after exiting the motorcycle, has to take a smaller road, and therefore he has to adapt the driving strategy to the new configuration. So you see that the same problem, you can view it as a static problem in which you are minimizing some parameters, but you can also see it as a dynamical system in which you are optimizing your driving or your control strategy. So there is not a unique formulation for the problems, and oftentimes calculus of variations and optimal control theory merge, right? And they do it in several ways. So one was simply the two different dual ways of viewing the refraction of light, either as a problem of the calculus of variation where you minimize time, or either like the driver problem in which you try to look for the shortest, path home, right? There is another link that appears when you are dealing with applications. Because, of course, in practical applications, right, when the systems get more complicated, things cannot be computed so easily. So here, the problem was that easy that we were able to compute very easily, right, the minimum of the function and confirm the Snell law. But when the function you are minimizing, J, is very complex, right, the explicit computation of the minimum will not be that easy. You can always say, well, don't worry, the minimizers is given by this equation, or maybe if you are dealing with some constraints here on the parameters U, right, you will do, like Lagrange multiplier and say there will be some Lagrange multiplier, and this will be G prime equal to, right, J prime equal to lambda G prime. But if J and G are complicated, you will never be able to solve these equations explicitly. We know we can solve easily quadratic equations. We have a formula. For cubic equations, the formulas for the roots of cubic polynomial equations are already more complicated. But if you take general transcendental formulas, nobody knows how to compute explicitly the solution. Actually, what you have there is you have other tools like the implicit function theorem or Rouchet theorem for, say, analytic function that will give you approximate solutions, right? In practice, you will not be able to find explicit solution. You will use the computer. So how does the computer do? Well, one of the say most fundamental ideas that computational mathematics have developed, right, is the so-called gradient methods, right? So what are gradient methods doing? Well, gradient methods are a substantial A, the most powerful, one of the most powerful tools in order to minimize a functional, right? So regardless of what the function is, you can always try to use a gradient method. So imagine, we are hiking, right, on the mountains of Changchun, right, and we get lost. We're here in this peak, and we got lost. I wanted to come to the back home, and I know my home is here on the valley, and I am lost somewhere in here. I want to come down home. So how will I do it? Well, I will probably implement a gradient descent algorithm, right? So this is a gradient descent algorithm, right? And actually, in this case, right, the one I am writing is simply the steepest descent algorithm, right? The steepest descent will be the faster. Sometimes it's going to be very complicated as well. It could be even dangerous because sometimes you are walking down, some hiking, and then, okay, you say, well, this is the steepest descent, but well, this looks like impossible. Let me take a descent direction that is not so steep. Maybe I will walk a little bit longer, but it will be safer, right? But if you just do it in the steepest descent, so of course for the computer there are not risky areas in which you risk to have an accident. So what you simply do, you say, okay, I start out of some U0, whatever the U0 is. The U0 can be anything. So I will start from here where I am, and then in the next step, what I will simply do, I will define U1 as being U0 minus rho gradient J U0. And then once I have U1, I will move to U2. And then, of course, I will have to take these steps rho to be small. So why is this a good idea, right? Well, the goal was to minimize the functional J, right? And you didn't know how to do it. So what do? Well, you try to build some iterative algorithm in your computer, something that you can very easily program in any computer language, right? And then you say, I take some initialization U0. Of course, if you have some intuition, right, about what the behavior of the functional is, and if you want to go down, well, maybe you better start from here and not from here, because you know that from here it will take you longer. But if you don't have any information, you just take some U0. So you take, for instance, U0 equal to 0. 0 is always a very easy choice, right? You take U0 equals 0, the one you like. And then you iterate, right? You iterate. My claim is that by iterating, you are going down. So why are you going down? Well, you can compute that very easily. Let me check that J UK plus 1 is less than J UK. Is this true? Well, I use the definition of UK plus 1, and I say, well, J UK plus 1 is J at the point UK minus rho gradient J UK. Rho is small, right? So this rho here is small. So because rho is small, I can define this, you know, I can approximate by Taylor's formula, right? Taylor expansion. This is going to be J at the point UK minus, right? Minus the difference rho gradient J UK at the point gradient J UK. Oh, then you see that here I get an square, right? Minus rho gradient J UK squared, right? And this is precisely why this is going down. But now, okay, of course you will tell me, yes, Enrique, but you forgot something. I mean, this is not exact, right? This is just an approximation. If I really check the error in the Taylor expansion, I know also that there will be a second term, which is rho squared, the gradient of J U squared divided by 2, and this will be multiplied by the second order derivative of J at UK, right? And this is where you see that you need rho to be small. Why do you need rho to be small? Because you need that the negative contribution of this term is more substantial than the positive contribution that the second order term introduces. And who wins, rho or rho squared? Who is more important, rho or rho squared? Well, when rho is small, rho squared is negligible with respect to rho. And therefore, when rho is small, I'm guaranteed that this is going down. So you see, this is the proof of the fact that the gradient of JUK goes down. Now, is a gradient system a good idea? Yes, it is. But you cannot always apply it. So there are situations like, and this is why Monte Carlo methods were introduced as well. There are situations you are facing some, you know, heterogeneous configurations in nature. There are some problems that are so chaotic, so mixed, like this kind of very, you know, heterogeneous pattern, right? This could be the skin of some animal, or, you know, the landscape, or some desertic, you know, area. You see there are two colors mixed here, blue and red. And then you see, if I tell you to optimize, this is like a labyrinth. You have to go out, and it's almost impossible to do it because, you know, things are so mixed that even, you know, when you are in red, as soon as you move a little bit, you will be in blue. It's really impossible to compute the gradient of such a function, right? Right? This is one of these functions that basically in practical applications, it will be discontinuous everywhere, right? Because wherever you stand, you move a little bit to the left or to the right, and you will quit from red to blue, or from blue to red. So it will be very, very difficult to compute any derivative. So here, you will not be able to implement a gradient method, right? So then what you do in those cases is to employ the Monte Carlo. This is the picture of the Monte Carlo casino, where you say, okay, I go to the casino, I bet, and I hope to be lucky, so to win, right? And then in those cases, when the functions are very complicated, what you do is you explore, you generate random numbers in the computer, you explore different configurations, and then you try to do better than before, right? So, and this is what, you know, happens when you are dealing with such a function, right? For instance, this function, okay. So we know this is the global minimizer, right? But, well, if really I don't have enough information, or the function here is so, you know, irregular, then computing derivatives is very difficult, right? What you will do is you will just, you know, run a Monte Carlo method, and then you will choose random numbers. So this one, or then I will see this number, this value of the function, and then you will give me the next random number is this one, and then you will give me this, and I will say, oh, when I compare this and this one, the second one is much better than the first one, so I'm lucky, you know? And then I go to the third one, and I get this one, and then when I get the value here, I see that it's there, I say, oh, no, in the third trial, you didn't improve. Then I go to the fourth trial, and I get it here, and then you get this, and you say, oh, this is even worse. You know, the second one was much better, right? And then you go for the next one, and you do this, and then you say, it's here now. Oh, it's still not better. But then you go to the fifth or the sixth or the seventh, and then you eventually get here, and then you see this point, and you say, oh, this is substantially better. Now the level of J, this is the graph of J, right? Now the level of J is much below the previous one. So I am already here. So I am at the minimizer. Well, I don't know. I mean, if you don't know the function, you don't know whether you are at the minimizer or not. Probably you are not. Actually, in this example, we know we are not at the minimizer. The minimizer is here. But certainly you have improved the original configuration. You were in this altitude, altitude, and now you are here, right? Now you are here, okay? So if someone criticizes the Monte Carlo method because, it converges in probability, but of course, after a finite number of iterations, you will never know how close you are from the minimizer really, is not as precise as a gradient descent algorithm. If someone criticizes Monte Carlo, you could also tell this person, listen, but when you are doing gradient descent, you are not guaranteed to converge to the global minimizer either. Because what does gradient descent do? Well, gradient descent, if you start from a point which is in here, gradient descent will bring you to this local minimizer, but it will never get you to this global minimizer. Why the gradient descent cannot, starting in this grid point, why the gradient descent algorithm is not able to bring you to this global minimum? Do you have some hint for this? Why the gradient descent will never bring you from here to here? If you initialize the process here, my claim is I will be trapped in this well. I will never be able to get here. Why is that? The step size is too small, says Yue Han. Thank you, Yue. Indeed, in some sense, what I have seen is that gradient descent, as the name says, is always going down with respect to the level sets of the function J. So if you start here, of course you go down. But once you get here, you cannot continue. The steepest descent algorithm will die here, will stop here. Why? Because if you want to improve this configuration and go to this well or this well or this well or the actual well where the global minimum is, in order to exit this well, you have to move up, and the gradient descent will never allow you to go down. You are always, go up. You are always going down. So you see that the inconvenience of gradient descent algorithms that are very precise, because you can really, apply Taylor expansion and guarantee you are going down, and you know how much you are going down according to the Taylor expansion and how big the step size and the gradient and the Hessian are. This deterministic algorithm that is so precise that it's a little bit bounded. It's bounded to live in a well. So of course, nowadays in machine learning in particular, where problems are so huge in dimension in data science, and you have to explore so many configurations, oftentimes the algorithms implemented are hybrid. Hybrid in the sense that the best you can do after you have seen the two presentations of the gradient descent and the Monte Carlo algorithm, the best you can do is to build a hybrid algorithm. Hybrid in which sense? In the sense that you will combine random search with gradient descent. How do you do this? Well, whenever the random algorithm gives you 1 point, you are here, you will apply, say, 5 iterations of the gradient descent, you will get here, and once you realize that the gradient descent is not improving anymore because you got to the depth of this well, this is when you will launch again Monte Carlo, and then you will explore a different world. And then you will do better here. This is like a, mathematician moving from one institution to another. You get the bachelor diploma in one university, then you go to another one for the master, then you go another one for a postdoc, and then you go for another one for associate professor, and then you are, exploring different scenarios in which your academic performance, right, can be optimized, right? This is what we actually do in most practical applications, and this is the optimal way of combining one and the other. And please recall that when we are dealing with the calculus of variation, optimal design, optimization, control theory, it's not that we are here to solve a tiny mathematical problem. We are here to provide optimal answers to complex, relevant questions. Okay? Let us now discuss more carefully about dynamic controllability. As I have explained before, although this is often, when we teach at university, the development of mathematics is presented in a coherent manner, things didn't occur that way. As I said, people were using derivatives and solving problems of the calculus of variations much before the concept of derivative was clear. So the same happened in machine learning control theory. So people were doing machine learning for many years. Actually, Controllability, the one we mentioned on the theory of optimal transport. Optimal transport is one of the key concepts and methodologies that is employed in machine learning. Many of the problems that nowadays, right, we address in the context of machine learning, when you talk to companies and they tell you, oh, we are using machine learning for what? Well, we have databases and we are doing this and that. And, if you are a mathematician, you will often recognize, well, but this is just optimization. This is just optimal transport. This is just computing extremals. This is, dynamic programming principle. This is optimal programming. So nowadays we call it machine learning, but before we called that field machine learning, that field was already being developed, was being created. The same happened in control theory. Control theory started with, these classical claims by Aristoteles, and, 2000 years later by these computations of Lord Maxwell on the stabilization of the pendulum. But it took some time until the field had a very clear shape, contour, and was recognized as such, right? So there is actually the concept of cybernetics that was coined by the French physicist Ampère, but it was only when Norbert Wiener, right, in his book Cybernetics, right, in the first half of the 20th century, right, he somehow recast the concept, he further developed it, and he defined cybernetics as the science of control and communication in animals and machines. So you see here some key words. You see control and communication, and this reminds us what we already have seen in the context of the harmonic oscillator. We said for the harmonic oscillator, we need sensors allowing us to measure the position or the velocity, but we also need actuators to actually apply forces on the system and modify the trajectory of the system. So you see that in the definition of Norbert Wiener of cybernetics, the duality between communication and control, the need of sensors and actuators to, efficiently control a system, it was already there. And you see also, this idea that animals and machines should be, in alliance, right? So animals can be humans, right? Humans, and machines can be computers, right? So you see this classical idea of Aristoteles of machines helping humans so that humans can be free, so that I can talk to you without paying attention to whether, you know, the air conditioning is on or off. So there is the thermostat is taking care of the fact that the temperature in this room I am now is convenient for lecturing. Okay, good. So cybernetics, therefore, was nowadays we identify cybernetics with robotics, with robots, you know, science fiction. But this is actually, you know, what nowadays control theory is, right? So, for instance, you know, we have seen how biomedicine has been substantially developed, so we can even, you know, develop bionic arms for people that have some, you know, genetic, you know, defect or have lost some arm on an accident. Now they can be, you know, empowered, endowed by this kind of bionic arms, which is certainly not like a real one, but is extremely helpful for those that are missing one, right? So this is a very clear application of all this work of, you know, wall of control, is this interface between control and medicine that is helping people to live better, you know, and undergo, you know, the difficulties that they can encounter in their lives. So now, how does it look from a mathematical perspective? So from a mathematical perspective, I will come back to this later today or maybe the next session where we will start doing, you know, more mathematical proofs. It's very interesting to see how Rudolf Kalman, who passed away 5 years back, he somehow formulated the problem in a mathematical way. So the statement I am, you know, referring to here, as you will see the next day, is very elementary. It's not that it's very sophisticated mathematics, but somehow the same as Cauchy was the one who said, well, people, you should stop trying to solve differential equations explicitly like crazy. You should rather think in terms of the Cauchy problem, right? So, and then Cauchy coined the concept of well-posedness for a dynamical system, right? So what is a well-posed dynamical system? You can check this in the Wikipedia. Well-posedness is, okay, you have a dynamical system in which you write the dynamics, x prime equal ax, you are given Cauchy data, initial data, x0 equal x0. You are living in a given, say, space. It could be a Euclidean space, it could be a manifold, it could be a Hilbert space, it could be a Banach space, and then you want that for every initial datum, there is a unique solution, and that this unique solution evolves continuously in time, remaining within that given, say, manifold or space you are given. This is the concept of well-posedness. And Cauchy was the one who said, stop trying to compute explicit solutions. This is something you will never achieve for complicated problems. Focus on solving the Cauchy problem, right? In that sense that you try to guarantee existence, uniqueness, continuous dependence, persistency in the space of solutions. So Kalman did the same work at the level of control. He said, okay, you have a Cauchy problem, right? So to begin with, you ignore the control. You have a Cauchy problem, which is given by these linear differential equations with constant coefficients. So in this case, x is a vector in Rn. So we are living in the space Rn. So x is maybe the temperature, as we said yesterday, in the different, say, offices of the math building in Jilin University, right? There are 100 offices. So x is a vector, x1 up to x100, temperature in each office. So n is equal to 100. Okay, so then, you know, this is a column vector. The velocity of x is a column vector. X is a column vector, and A is an n by n matrix. So it's a matrix 100 by 100, the square matrix, right? And this matrix is somehow linking, is giving me the connectivity between the different rooms, right? So for instance, if I am in my office and you come to my office, I will ask you, could you please close the door, right? Because otherwise the hot air outside will come into my room and I will lose the refrigeration of my air conditioning device, right? So A is the connectivity, how temperature is being, transferred, diffused from one room to another, right? And then the bigger the connectivity between two adjacent rooms is, the stronger the corresponding entry on the matrix A will be. And the weaker it is, the closer the corresponding coefficient will be to 0. Okay? So this generates a dynamical system. And in principle, in this dynamical system, there is no control. If you start this system out of an initial datum x0, then you will generate, right, the corresponding solution, right? And the corresponding solution will be as xt exponential at applied to x0. Okay, good. But now we have the opportunity to control the system. So this was about temperature in the building. Now I have the possibility to use the heating or the air conditioning system in the building, right? And I do it through control. I can inject hot or cool air, right? U depending on T. And this control, so this force, this source I am injecting into the system, of course, will modify the free trajectory that was, in principle, completely determined by the Cauchy problem. If I don't add any source U, I know the solution will be exponential ATX0. But now I am playing, I am forcing the system, and I am actuating on the system. So you see now the actuator is B, right? B, which is now a matrix N times M, right? M in practical applications is much less than N, because N is the number of components of the state, and M is the number of controllers, right? And normally, so this is like doctor, you say, well, so how many people are living in Changchun? So 10 million people. Okay, you don't have 10 million doctors. You have 10 million people, but maybe you have 1,000 doctors. So one doctor is taking care of 1,000 people. The same at university. We have, in Autónoma of Madrid, where I was yesterday, or in Friedrich Alexander University in Germany, in both of them, we have about 40,000 students. But we don't have 40,000 professors. We have much less professors, right? So the same happens here. So normally you have to regulate temperature in a system of dimension 100, but you don't have 100 actuators. You have much less. So you have a centralized air conditioning system, and maybe one single control is able to regulate temperature all around. But in order to do that efficiently, of course, you need a good design of the circuit for, the distribution of cool air within the building. And this system has to be designed in an intelligent manner. This is optimal design, because probably that the upper floors will be hotter than the floors below, and therefore you need to guarantee that there will be enough strength in the compressors to push, cool air up to the upper floor with sufficient intensity, so that in the upper floor, which is those that are hotter, there is enough cool air arriving. Okay, so you see that in practical applications, it's not only about saying, oh, I do either active control or passive control. You have to do both. You have to do optimal design. You have to do a good passive control to guarantee a very well-performing, system. This is like when you buy a car. You want a good car which is safe, which is not very noisy, which is comfortable, which is stable, which is secure, which is fast, which doesn't, consume too much gasoline, because gasoline is expensive, that doesn't pollute a lot, because we have problems of pollution in cities. Okay, so you need a good passive design, but then you need also an optimal, actuation on that system. So in this system, A is the free dynamics. There is nothing you can do about A. A is meteorology, A is wind, A is traffic, right? And B is the control actuator. So of course, for once the system is designed, if you give me the A and you give me the B, the only thing I can tell you is whether this system is controllable or not, right? But in practical applications, as a control scientist, very often the question that you will be formulated will rather be, okay, we have this system. Could you please tell me how we should control it? Therefore, the question will be double in the sense that you will be, asked how to design the B. And then once you design the B, how, you use the control the U, right? So this is like when you are buying a TV, depending on which room you are placing your TV, you will choose a smaller TV or a larger TV. If you are, you have to buy a TV for a large auditorium for 1,000 people, where you are following Zoom conferences for 1,000 people in a large auditorium, you will need a very large screen. But you will probably not take such a large screen to your room, right? Where you just want to watch a movie before you go to sleep, right? So you make the proper choice of the B, right? You make the proper choice of the B, but then you have to do the optimal actuation through the U. So how do we formulate the paradigmatic problem of controllability? So this is one of the central ideas, right? Very much related to optimal transport, very much related to allocation of resources, very much related to machine learning. When you want to, given, a data set, you want to do an optimal classification, like in your computer, right? Where you open, the photo folder, or you say, oh my goodness, I have 10,000 photos. I have 10,000 photos in my photo folder, but they are all disordered. I would like to put some order on it. So what do I do? Okay, so I say, I identify people. I say, this is myself. This is my colleague, Professor Kai Zhang, and this is my other PhD student, and this is my PhD advisor, and this is a colleague I met in a conference in Paris, and so on. You put the names to these people, and then you ask the computer, please classify, and then the computer will start working and will identify and will put all these 10,000 photos in 100 folders. The 100 folders of the people you have chosen. Why? Because it will make comparison and will set up classes of equivalence so that all the photos of myself will be put in the same folder. Different ages, different locations, different situations, different dressing, right? Glasses, no glasses, all of them will be put in the same, equivalence class. So this is also a controllability problem. This is why you see that, control and machine learning and the modern applications of machine learning, for instance, supervised learning, classification, are very much related. After all, you are trying to do very similar things. You have a system on a given configuration, and you want to drive the same system to a different configuration. You want to, out of this folder of 10,000 very unstructured photos, you want to put them in a very well-organized folders, okay? So back in the 50s, when the term machine learning was not yet coined, people were already doing machine learning, but for them it was control theory, right? And then the way the controllability problem was formulated was the following, people said, I will say that this differential system, this differential equation, driven by the matrix A, with the control matrix capital B, capital A and capital B, right? The system is controllable if in a time window 0 capital T, sometimes you have a very short time window, some other times you have a longer time window. This is like when you go to the exam. So some professors, they will tell you, no, we do very short tests. We will have 40 minutes for the exam. In some other cases, they will tell you, no, we are doing long exams. You will have 3 hours. So sometimes, the time window is short. Some others, the time window is longer. Okay, fine. Given the time window 0 capital T, the question of controllability I'm looking at is whether, given an initial configuration x0, right? Okay, I can guarantee that the system can be driven to a final configuration x1. So given any x0 and given any x1 in the time given capital T, can I find a control U that will drive the system from x0 to x1? This is what we say controllability, right? And then, the answer by Kalman was, a system is controllable if and only if this purely algebraic condition is fulfilled, right? So the only thing he said you have to check to see whether a system is controllable is whether the rank of this matrix B, AB, AN minus 1B is equal to N. So what I'm doing here, you see, take, for instance, the extreme case where M is equal to 1. This is always the most interesting and the most challenging case, right? So you see, in that case, the control UT is just a scalar. So you only have one actuator. And because you only have one actuator, this is like the temperature in the thermostat. There is only actually one actuator. You just choose temperature. You don't even have the intensity of the fan or the winter and summer mode. No, it's a very simple thermostat. Just one actuator. Just regulate temperature. Okay. So just one actuator, UT. And with one actuator, UT, now the matrix B is what? The matrix B is actually a column vector, right? Which is a matrix N by 1. So this column vector, right, B, is taking the scalar control you are choosing, just some intensity, 1, minus 1, 10, minus 10, 0, if you want to stop for a while, right? So this scalar action is distributed into the n components of the system through the vector capital B, so that every component of the system will be affected by U differently. So when the component B1 is very large, this means that the component X1 of the system is very sensitive to the action of the control U, in the sense that the action of the control U will be amplified, will be multiplied by B1, and this will be impacting the dynamics of the first component X1 of the system very directly, because this enters as an additive term on the derivative of X1. Maybe this happens for some components B, X. But now maybe for another, right, maybe Bn is equal to 0. So what does it mean Bn is equal to 0? Well, Bn is equal to 0. It means that the action of U has no direct impact on the last component Xn. So it means in the last room, there were 100 rooms in the, there were 100 rooms in the building, and someone forgot the last room. So air conditioning is not getting to the last office, right? So Bn is equal to 0. Yet it doesn't mean that there will not be an impact of the refrigerator system on the last room, because of course by diffusion, the cool air that is getting to the, to the 99th room will also diffuse a little bit to the 100. But this is a secondary effect that will be seen only on the interaction of the different components of the system. What the, the control operator B is telling you is simply how the different components are being affected directly by the action of the control. Okay, good. Now, what Kalman said, the system is fully controllable. We say simply controllable. We should say exactly, completely, fully controllable when you can do whatever you wish. I mean, in the absence of constraints, right? So if you have as much energy, as much electricity as you wanted, right? This controllability property guarantees that you can drive the system from any initial configuration to any final one, right? And the only thing you need to do this, according to Kalman, is that the rank of this huge matrix is equal to n. But what is this matrix? You see, in the first term, I just put B. B is the column vector. In the second term, I put what is AB. If B is a column vector and A is a matrix n times n, AB is another column vector. So here I have n times 1, a column vector, n times 1, a column vector. Here I have n times 1, a column vector. How many of them I have? I have power, you see, power of A, n minus 1, power of A, n minus 2, power of A, n minus 3, power of A 1, power of A 0, A to the power 0 is the identity, so it's not even written because it's just the identity. So you see you have here n times. And because you have them n times, all this huge Kalman matrix is a matrix n by n. So the only chance that the rank is n is that when you really, compute the determinant, you get something different from 0. This is a purely algebraic condition. What you see in this statement is that in principle, checking whether a system is controllable is very simple. It's just a matter of linear algebra. You build this big matrix and then you compute the rank. And of course, when you open the MATLAB toolbox for control, of course, this is one of the commands you will have, right? One of the commands will be the computation of the Kalman rank, right? Because this is the one that will tell you whether a system is controllable or not, right? I mean, this is certainly much better, right, than doing it yourself. You don't need to compute the rank yourself. You simply say, okay, to MATLAB, I have this system, this control system. Well, this is my matrix A. This is my matrix B. I would like to know whether this system is controllable. And then you let the MATLAB command to compute, the rank, and the Kalman, command will tell you, oh, the system is or is not controllable. Now, when the rank of this matrix is n, the system is fully controllable. What do you think it happens if I compute the rank and I don't get n, I get n minus 1? What do you think it happens then? Can you please tell me? What happens if, right, I don't get n, but n minus 1? What do you think is going to happen? According to Kalman, the system is not controllable. Yeah, Yao Huang. Thank you, Yao. Indeed, the system is not controllable, but what is the difference? So does it make a difference that the rank is n minus 1 or n minus 2? Does it make a difference, n minus 1 or n minus 2? In some sense, the lower is the rank, the less the system is controllable. Okay, good. Let me explain you this. So we look to, there is a very interesting book. You can download the PDF of this book. I mean, this is one, is now 23 years old. I think Eduardo Sontag is a senior professor in the US, a very well-known expert in control theory. I think actually he was a PhD student, former PhD student of Professor Rudolf Kalman, I think, right? And in that book, other than the theory of control for, dynamical systems and also for discrete systems, right? You will also find there, applications to neural networks, so kind of techniques we employ nowadays in machine learning, as I mentioned before, right? At that time, this theory was not called machine learning, but people were already doing machine learning, right? You have a very classical applications like this one about the Nelson car. So don't ask me why this car is called Nelson, but probably this is certainly not a car brand, right? So this is not a Volkswagen, or right? So this is just probably Nelson was a mathematician that was trying to analyze whether how efficient it is to drive in a car, right? By mathematical control theory, right? And he said, okay, how do I model a car, right? I do it in the simplest possible case. So I take a car, which is just flat. So I'm not thinking in 3D, I'm just thinking in 2D, right? So I live in flat land, right? So I just look to a rectangle. The shape of the car is a rectangle. So he said, Nelson said, how many parameters I need in order to determine the position of the car? Well, I need, x1, x2. So the position of the center of gravity of the car, I need 2 parameters. But I also need the orientation of the car, right? So I need an angle phi, which is giving me the orientation of the main axis of the car with respect to the horizontal. This is the angle phi, right? And then I also need the angle of the wheels theta. I need also the angles of the wheel theta with respect to the main axis of the car. So I have 4 parameters. So here n is equal to 4. There are 4 states on the system. So x1, x2, phi, and theta, right? So this is going to be the state of the system, right? Of course, you could say, well, I am interested also on the velocity. Then you could add 2 more, right? Or more angular velocity and so on. But let us make it simple. If you just think on, I take a photo of the car, right? I like to know where my car is parked. So I take a photo. These are the 4 parameters I need. And now you say, how many controls do I have when I am driving a car? Well, I have the acceleration, right? So the acceleration, so I can regulate the velocity. And by regulating the velocity, right, this is like the harmonic oscillator, right? This is a second order system. I'm not acting on the velocity. Of course, the velocity of the car changes, but I am actually acting on the acceleration. So I am acting on the second derivative. The change on the second derivative induces a change on the velocity on the first derivative. And this change on the velocity induces also a change on the position, right? So when I am on a rush, I will accelerate more. But when I am getting close to a traffic jam, or close to the downtown, or close to the destination, I will slow down. I will decelerate. I will brake, right? Okay. So how many controllers I have? I have acceleration, and I have also the gear. I can also regulate, right, the angle of the wheels. So I have 2 controls, right? So controls, I have 2. So it means that m is equal to 2. So this is a typical situation where you see that the number of controls is less than the number of states. Despite of this, I am able to drive the car. So the car is controllable. Right? So you give me a car, if this is in a flat space, if there are no obstacles, then there is no problem. I can control the car. Of course, if you put too many obstacles, right? This happens in some parking places where there are many columns, right? And then it's very hard to park, right? In particular, if you have a big car, well, it will hardly go through. But this is different. I mean, there are obstructions there, right? So I'm not considering this. In the context of the Kalman problem, we assume that we are working in a, in a space without constraints. I'm just, wondering whether I can control a system right? In which I have 2 controls and 4 dimensions, and then I can. Now, but assume that I was considering this car, I say, well, you know, the car is flat, but I'm living in the 3-dimensional world. You see, I have 3 dimensions, vertical, horizontal, width. We are living in a 3-dimensional space. So then I say, no. You know, the car is located at, the car, right, had, right? You said that the car had 4 components. I say there are 5. There is also the height, right? Okay, now in this case, n will be equal to, right, 5, but I still will have only 2 controllers. Will the car be controllable in a space? Well, clearly not. I mean, the last component in the car is not controllable. There is nothing I can do in order to regulate the, you know, the height of the car. I mean, a car cannot fly. If I really want to move in the vertical direction, I don't need to buy a car. I have to buy an helicopter, right? And this is much more expensive and also harder to manipulate, right? If I have a car, I can move in the, you know, on the horizontal plane. So with m equal to, I can guarantee the control of 4 components, but not of 5 components, right? I don't solve anything by saying that I am merging, embedding these dynamical systems into 3 space dimensions, because, you know, wherever I do, the rank I will get will be 4. So this is a typical application where you see that regardless how rich the modeling is, you can claim that you are working, you are living in the 3 space dimension. Yes, fine, you can do it. But when you compute the rank of this control system, right, with m equal to, you will only saturate a space of dimension 4. Therefore, the Nelson car is controllable in the sense that you can put the car in from any configuration into any other one, right? Located where you wish, oriented as you wish, and with the wheels also with the angle you wish. You can do that, right, on the plane, but please don't ask me to move in the vertical direction. This car will never fly. So the rank will be 4, but it will never be 5. So this is why I was saying, when the rank is n, the system is controllable. When the rank is less than n, you can say that the system is not controllable, but you can say more. Because if when you compute the rank, you get that the rank is n minus 1, you will say, well, the system is not controllable, but only 1 dimension is missing. All the components of the system are controllable except for 1. But when you compute the rank and you see that the rank is n minus 10, you will say, well, no, bad news. Out of the n components of the system, n minus 10 are controllable, but 10 of them are not controllable, right? So you see that this rank test is not only good to discriminate, you know, whether a system is controllable or not, but actually it's even better because within the class of non-controllable system, it will allow you to tell you what is the defect, how much, by how many dimensions you are missing the system to be fully controllable. Okay, good, very good. So let me show you how things work, right? So actually, this is a drawing I took from a previous lecture series that Jean-Michel Colon delivered in Bilbao 10 years back, right? And this is the drawing he did. You know, when you are parking, for instance, and unparking the car, this is what you often do, right? So assume your car is in the street, right? And is parked. and you have a beautiful, right, limousine. This is your car, right? So this is your car. You have bought a very, expensive limousine, right? And you have to unpark the car. What do you do normally? Well, normally what you do is you move forward and you turn right, and then you move backward and you turn left, right? And you see, it takes some time, right? So when you wanna get your driving permit, so here in Europe, you take about 20 classes. And one of the most difficult exercises to learn is how to park and unpark a car. And it's actually not very intuitive. Why? Because you are doing and undoing the same thing. You move forward, left, backwards, right. So you say, well, I'm doing and I am doing. So I'm moving forward and then backward. I'm driving left and then right. So why I'm doing this? Well, it's because, the operations of moving forward and driving left, moving backward, and then driving right, they are not commuting. And it's because they don't commute that you are able to, out of this apparently a stupid exercise of doing and undoing, because the different components of the system, of the actuation of the system are not commuting, what you succeed is that you are able to bring the car back to the same position. So the center of gravity is located in the same location at the same place, but the angle has changed. Now, obviously, once you have done this, you are still not free, right? So this car could not exit. If you will try to exit, you will collide here. So you need to iterate again and again. And why is that? Because, the fact that the two operations are not commuting, they give you simply a second order effect. Meaning that if the amplitude of your action is epsilon, right, the gain you have on the improvement of the previous configuration is epsilon squared. This is why when you are parking, if the room that is very narrow, if this room is very narrow here, you will have to iterate many times. Why? Because if the room is very narrow, it means that the amplitude of the controls you can use is just epsilon. But it means that even if you do it very well, after the first iteration, the gain will be, epsilon squared. Epsilon will be the amplitude of the control, right? The amplitude of controls, but the gains will only be epsilon squared. So you will need to iterate again and again and again. This is like when you are dealing in a machine learning problem, you have many photos to classify. Well, you will have to iterate many times. I mean, if you you don't believe that, just try yourself. Try to classify the photos in your photo folder manually, and you will see how much time it needs. You will first say, okay, I will classify the photos of myself. So I will build a folder, Enrique, and then I go to the first photo, I put this or not, depending on whether I am or not. But then when I am getting, to the end, I will have to check the different folders, go back and forth, and this will be extremely time consuming. The same here. The smaller is the epsilon you have for the amplitude of the control, the smaller is the gain, epsilon squared, and therefore you will need more and more iterations. Okay? So actually, this is something which is also reminiscent of the Kalman rank condition. It tells you, you see, in order to check whether a system is controllable or not, you have to compute a very large system. Actually, there was a question here by I think it was Zikon Sang, who was saying, well, I said that when m is equal to 1, right? When m is equal to 1, in here I have, say, a column vector n1. Here I have another column vector n1. Here I have another column vector n1. But what happens when I have two controls? So what happens when I have, for instance, two controls? Now I have two controls. So not only I can, regulate in the thermostat, I can regulate temperature, but I can also regulate the intensity of the fan. How intense is the flux? Not only the temperature of the injected air, but the volume, of the injected, say, air. Then I have two controls. So in that case, m is equal to 2. If m is equal to 2, then if m is equal to 2, when m is equal to 2, the control B now is a matrix which has, two column vectors, B11 and B2, right? B1 as a column vector, B1 as a column vector here, B1, and B2 as a column vector. So now this matrix B is going to be n times 2. And the matrix AB, when I multiply a matrix n times n with n times 2, it will be also n2. So in total, this matrix will be n times n. So then, of course, when you have more controls, the chances of controlling the system will increase, right? Why? Because now the dimension of the system, right, is n times m. And there are plenty of possible choices of square submatrices n times n, so that, I can fill the rank equal to n. And it is sufficient that there is just one possible choice of the columns, right? Out of these n times m columns, I have to choose only n of them. This is a combinatorial number. It's just one of these choices of the columns produces n as a rank, then the system is controllable. So why is that? Well, because there are many ways of, driving a car. And actually, you see when people are parking or unparking, you see people that are very expert, they do it very smoothly. And then in one iteration, the car is parked. And there come some other people which don't have that much experience on driving, and they need to do 10 iterations to park the car. Why is that? Well, because there are many ways of controlling a system when the system is controllable, right? Then here, if you are smart, right, you will do it very simply, or maybe you will do it in a more complicated manner, right? But this is because when a system is controllable, there are many ways of controlling a system. So in this characterization of Kalman, they don't tell you how to control the system. They tell you whether you can or you cannot. If the rank is n, you can always control the system, but you have still to find the control. And out of the many controls, you have to find one that is optimal. This is one, when there is a Formula One race, there is a winner, and one, some other is the second, the third, and so on. One is driving optimally, the others are suboptimal. Okay? Good. Oh, another important remark. You see, this is kind of paradoxal. We say, this is a dynamic control problem, and the time horizon is very important, right? So for my class, it's very important for me to organize my classes. I need to know how much time Professor Kai Zhang is giving to me. So he was very generous. He allocated sessions of 3 hours. So I can prepare the material. I know in 3 hours I can say a lot. Good. 3 hours. So time horizon equal to 3. But it could also be that Professor Kai Zhang says, no, we are rushing, so today you only have 1 hour. Oh, could be t equal 1. So how I manage, how I control a system, how fast I go, how condensed I present the material, will certainly depend on the time window. But it turns out that when I look to this Kalman characterization, the time window doesn't show up. How can it be? Time is essential on the dynamical formulation of this control problem. How can it be that time being so important in the problem formulation, it doesn't show up on the answer to the question? Why do you think time has... There are questions about this actually by Sala. Is the independency of T intuitive in this setting? Is it intuitive or not? So what Kalman is telling us here, and it's actually what we see in the Nelson curve, is whether in the system, by manipulating the different controls, all kind, like in a cubic Rubik cube, whether all kind of possible combinations that I can do of this Rubik cube, playing with the different controls in the different directions, switching in time, whether, right, this can solve the problem or not. If the rank is n, all combinations fill the whole Euclidean space and the system is controllable. When the rank is less than n, n minus 1, or there are some dimensions in which I am blocked, like the car on the space. The car can move freely on the surface of Earth. The car cannot be transported vertically. One direction is forbidden. The rank will be n minus 1. But time doesn't show up. Why? Why do you think that the time doesn't show up in this Kalman characterization? Actually, what this characterization says is that if a system is controllable in time 100, the system is also controllable in time 1 or in time 1 over 100. The controllability of the system does not depend on the length of the time horizon. Why do you think that is true? What do you think? When I am controlling in a short interval or in a long interval, when do I need bigger controls? When do I need the controls to be larger? In short time horizon or in long time horizons? This is like when you are preparing an exam. Yeah, in short time horizons, of course. Thank you, Yue. When the time horizon is short, the control has to be much stronger, right? So if you have to prepare an exam, oh, the exam is tomorrow. I didn't do anything until today, so I just have 24 hours to prepare one full semester exam. You better work hard that day. I mean, you stop, you don't go with your friends to the coffee shop, you don't go to the swimming pool, I mean, you don't watch TV, you stop chatting with your telephone, you just focus and concentrate and work hard 24 hours. Now, if you have 1 month to prepare just one exam, you can take it easily. You say, well, I will devote like 2 hours per day, that's more than enough. Okay, I have like 2 days per lesson, there are 15 lessons, I have 30 days, 2 days per lesson, I just do 2 hours in the morning every day, and that's fine. So, of course, whether a system is controllable or not doesn't depend on the time window, but of course, the intensity of the control you will use will very much depend on how long the time interval is. That's the point, okay? Let me now show you how things work in practice. Yeah, of course. So that's a very good question by Ma, right? So typically, I will come back to this topic later. This is very important, right? But normally, depending on the time horizon, if you draw here how big the control is, then typically this will be the situation, right? So, right? You will have a polynomial blow up, right? So the size of the control will grow up polynomially, right? There are, very classical results, for this, right? Typically, it will depend on the dimension of the system and the rank and all this. So this blow up will be typically polynomial. It could be something like t to the power minus n, right? If you are, you have just one control to control a system of n components, when the time is very short, right? When the time horizon is very short, the size of the control will be of the order of c capital T to the power minus n. When you are dealing with infinite dimensional dynamical systems like the heat equation, for instance, and you can see that easily on the Gaussian, say, fundamental solution of the heat equation, the control time will blow up exponentially, right? Okay, but when the time window is very long, right, then the control size will go down to 0. The longer is the time, the more efficient it is, right? So then when you look nowadays to the, to the main applications of machine learning, like, DeepMind, I mean, these machines that are able to win to the world champion on checkerboard or Go. I think now the machine can even defeat the humans in Go also, right? Go is more sophisticated than checkerboard. It took more time. But I think now the machine can always defeat humans even playing Go, right? Yes, but I mean, you have time constraints, right? Right? When you are playing checkers, I mean, you have a few seconds for every move. You don't have an infinite time horizon. Of course, in an infinite time horizon, you will compute a lot, right? You will not need such a big machine or performant algorithm. You will always win with the machine. The challenge is that you have to do it within given time windows. And then the cost of control is very, very strong. And this is why you need a very powerful, say, RAM, right, hardware, but also very intelligent software, because you have to find the answer in a very short time, right? Okay, but this is the generic answer. Good. Let's see how it works in practice. So let's see how you park a car, right? Of course, I mean, the answer normally to the question about the restriction is that if in practice, right, if you understand that this is the kind of shape on the cost of controlling the system, if in practice there is a threshold, right, if I tell you, listen, this is the money I have, this is how much energy I can use, this is how much, gasoline I can put on my car. What this is telling you, well, in that case, if this is the threshold, the constraint, the upper bound on the control, then the answer will be, okay, so then you have to give me that much time. It's like when you are doing some renovation at home, then you bring, a person, you say, okay, I would like to renovate the kitchen and the toilet and paint and change the windows. They will tell you, okay, yeah, but we need 1 month. And you say, no, I want it in 1 day. Well, in 1 day is impossible. We are just 2 workers in my office, 2 people working here. We need 1 month to renovate your apartment. If you just want it in 1 day, then you need to buy and, hire another company where maybe they can put 20 people and then in 1 day they do all, right? So depending on the threshold you put on the control, typically this will give you a constraint on the time window. So you can read this kind of graphs. That's important. Thank you for the question. That's important. You can read off this graph in 2 dual manners. Given the time window, I will tell you how expensive it will be, but also you can read it in the dual manner. If you give me how much you spend, I tell you how much time you will need. Okay, let's now see the control in action. This is a very simple exercise. I mean, everyone that drives a car knows how to do this. So you are parked here, right? And you have to bring the car from this parking lot to this other one, from this position to this other one. But the car is constrained to live in this square, right? So you cannot go out and then come and then right? This will be a very long path. You are not interested on doing this, right? So you want really to do some kind of optimal transportation. This is optimal transport from this position to that position. How do you do it? Well, you will do something like this. You first move forward, and then you come backwards. Okay? Now, if you have more, I mean, now you are not driving a simple, automobile, a car. Rather, you have a truck, and the truck is articulated. It has 3 bodies, so this is like a train, right? And then you have to move this truck from this configuration to this other one. So this one, more or less everyone with a driving permit can do. This is a very simple exercise, right? So you go forward right, backward left, and if you do it in an intelligent manner, indeed, you will bring the car from the initial position to the final one. This is a very simple exercise. But doing it with this kind of articulated multi-body car, it's much more complicated. You can still do it, right? And then you will write your model. You will ask MATLAB to give you what is the optimal trajectory for controlling this dynamical system from this configuration to this other. But you will see something much more complicated, right? Because now, right? And this is why the traditional driving permit for a motorcycle or a small car will not be legally valid for driving such a complicated, articulated car, is because, the difficulty in here is that when you are thinking on how do you guide, you are sitting here, you are acting on this piece of the car, you are acting locally, but you have to anticipate the oscillations that the motion of the main body here in front will induce on the other pieces of the car that are coming afterwards. And this is where, why you see, that this motion is much more sophisticated, because the motion of the main body is inducing all these oscillations on the back pieces, right? So this one will be much more complicated. Okay, so there are other people, however, that are trained with in different, say, auto schools. So this is the Kung Fu auto school. So if you are able to, to take your driving permit in the Kung Fu auto school, then things will be much easier, because you could, you will be able to park the car in a much more straightforward manner with such a sophistication of the Kalman, say, brackets and iterations, right? You can just do this, right? So you just exit the car and then you push it, okay? And that's it. This is a different way of parking, okay? But this normally is not accessible for normal people. This only very few experts are able to do it. Okay, good. Optimal design. We mentioned that too. We said active control. So you see, this is very active control, right? So here the action is like a Dirac delta, short time interval, the straightforward control. This is Dirac control, impulsional control. But we talk about active control, but we talk also about passive control. So optimal design. What is optimal design? Well, optimal design is like cooking, right? So, what are the best ingredients for a, for a Sichuan very spicy soup? Or what are the optimal ingredients or cooking recipe for an optimal pancake? I mean, this is written, right? So when you open a book for cooking book, then they will tell you, okay, you have to buy these ingredients. This is the volume of the ingredients, and then this is the way you have to boil them, cook them carefully. This is the temperature you have to choose. This is the time you have to put it on the oven and so on in order to get an optimal cooking. And if you do an optimal cooking, then you end up with a beautiful campus, right? So I have not been in the campus of Jilin, but I was checking yesterday photos of the campus, and I see that this is indeed very beautiful. I don't know whether, you can see the map building here somewhere, but it is certainly a very beautiful campus. It's optimal design from an architectural point of view, an urban point of view. You see the trees, you see the nice buildings. This is a very well integrated, optimal design from the perspective of the urban and architectural planning, right? So how do we do optimal design? So very often humans, they do optimal design by inspiration, by imagination, but oftentimes we just doing it mimicking, right? We just doing mimicking nature. So for instance, when we design aeronautics, right? When we design the modern, say, airfoils, we are just trying to copy with what a simple bird can do, right? So we are the most intelligent, living species in the planet. Yet when we see how birds fly, we wish we could do it the same way they do, right? Or when we see a fish swimming, a whale or a shark or a tuna or a small anchovy swimming in the sea, we wish we could do it in the same way. They are much more, performing much better than we do by swimming. Regardless of how much we exercise, we will never swim like a fish. Regardless of how far aeronautics evolves, we will never be able to fly like the birds. So what is our point of view? Our point of view is that of optimal design, optimal control, controllability. All these things are mixed. But you see, they are mixed in different phases. There is one initial phase in which the airplane has to be designed, or the car has to be designed. So in this initial phase, the airplane or the car are designed based on geometric concepts. So you are designing the airplane or the car in order to minimize drag, in order to maximize stability, in order to maximize the sustainability, right? So you want, the airplane or the car to be designed so that it can travel fast with a maximal stability and a minimal oil or energy consumption. And this requires that the shapes are computed optimally. This is why, by the way, the shape of a Formula One car is not the same as the shape of the car we buy for driving in, from home to, to the university campus. Of course, the goal is not the same. The Formula One car has to drive 300 kilometers per hour. Our car will drive, so basically 100 kilometers per hour, maybe, or even less if you are driving in the town. So you need something which is more comfortable than fast. While when you are driving a Formula One car, it doesn't look like very comfortable, right? When you see the Formula One driver is, collocated in a quite, gymnastic position. He's a sport person, right? You have to be very strongly trained in order to be a good Formula One driver. It's not just having the license. You need to be really very fit to drive a Formula One car, right? Because, the requirements are completely different. So here the requirements is more stability and velocity. It's not about comfort, right? Okay, so we do that, we need to use computational fluid dynamics. And you say, well, why do I need to use computational fluid dynamics? I just wanted to design a car, right? So the designing a car, it should be something like making a nice drawing, right? It's just something about, being an artist. No. It's not only about being an artist. It's not only about being an artist. You have really to compute the drag. You have to see you have to see in these simulations, you see already how, the point of view we adopt when we are doing mathematical analysis of this problem is that of the wind tunnel, right? Of course, the car is moving very fast, but we are working in our office. We cannot run after the car. I am standing in my office. My computer is fixed. So I cannot be running after the car. So I have to see the car in my computer. So we adopt the point of view of the wind tunnel, right, through computational fluid dynamics simulations, in which we think that the car is fixed in our computer, but because the car is actually in reality traveling 300 kilometers per hour, what I try to simulate is this scenario in which the car is fixed and the wind is traveling 300 kilometers per hour in the opposite direction. Due to the geometry of the car, this will generate some air currents, this will generate some turbulence, and the more turbulent, the more chaotic these lines of wind are, right? The particles of air are moving, the more turbulent, the more chaotic, the more rotational, the more curl there is in this turbulent airflow, the more unstable, the trip of the car will be. So in this way, adopting the viewpoint of the wind tunnel and using the tools of computational fluid dynamics, because I have to solve, the Euler or the Navier-Stokes equation of air traveling 300 kilometers per hour out, surrounding this obstacle, because the car then is like an obstacle that is, making impossible, right, the wind to travel through, this solid obstacle, right, that the air cannot penetrate. So because of that, right, I need to use computational fluid dynamics. And once I have, the computation of a shape, right, I would like to improve. I will say, well, the performance of this car is good, but maybe it's not as good as the one by Ferrari. If I use this car on the race, I will never win. So I need to improve this shape. So how do I do it? Well, I do it using the tools of, say, optimal shape design, which are basically the tools in which, once again, I am minimizing some functional, which depends on the shape. So omega is the shape of the car or the airplane. And this functional that I am minimizing, it will be a sophisticated functional, which will be multi-criteria, right? Because it will have to take into account the different ingredients, the different key parameters, the different, say, motions that are interlaced, elements, effects that are interlaced when defining, right, the motion of a car or an airplane. In particular, I will have to take into account the drag, the thrust, and the lift. Okay, so this will be a multi-criterion optimization problem. But once I have defined this, how will I manipulate? How will I improve the shape? Well, I will do it as in the gradient descent algorithm. I will improve the previous shape omega k by just computing the gradient of the functional j with respect to the shape. Okay, so this is what is called the shape design analysis, and it could be optimal when we are trying to optimize it. Of course, in practical applications, you never get to the optimal shape design. The optimum is something asymptotic, right? We are just improving generation by generation. When you look to an airplane today and you compare it to the airplane in the 70s, you see how much aviation and aeronautic design has evolved in 50 years. You also see on the traditional automobiles, actually, you certainly see it also in China. I mean, here in Europe is very obvious, right? 50 years back, the Renault cars and the Volkswagen cars, for instance, the French cars and the German cars were very different in shape. Nowadays, you see how all of them are converging into similar shapes. Why? Because basically, all producers of cars are basically using the same functionals in order to optimize the shape of the car. And even though they started from different, say, very different initializations as shapes, because originally the initial shapes of the cars of the different brands, Renault, Volkswagen, Fiat, and so on, right? They were quite artistic and very different. Now, by optimal shape design iteration, by applying a gradient step descent iteration, they are all converging to similar shapes. Okay, good, very good. But now, as I said, it's not only about the geometry. If you want to really solve this problem, right, you have to compute the gradient of this functional, and this functional is quite involved because you have to really, for every shape, you have to compute the flow of air around that shape. And this requires solving the equations of fluid dynamics, either Euler for perfect fluids or either Navier-Stokes if you are taking into consideration the viscosity of the fluid. And this can be something very complicated, right? So you need a very sophisticated numerical solvers in order to be able to get accurate numerical computational approximations of turbulent, say, regimes of airflow that are generated when you are really dealing with, a problem in true aeronautics. And this is where science gets more and more sophisticated, but also fascinating. So you see, this is kind of contradictory. Aviation works very well. There has been a huge evolution on the improvement of the shapes of airfoils, right? And we do that combining the ideas we have mentioned here of optimal shape design, fluid dynamics equations, Euler and Navier-Stokes, and computational fluid dynamics, which is numerical approximation schemes for the partial differential equations of fluid dynamics, Euler and Navier-Stokes. You say, oh, we have been very successful. Yes, but only partially, right? Because when you look to the 3 millennium problems of the Clay Foundation, right, you realize that out of the 7 millennium problems that were defined by the Clay Foundations as the main challenges of mathematics for the 21st century, you realize that only the Poincaré conjecture was solved back in 2006 by Grigory Perelman. The 6 other problems are still open, and one of them is Navier-Stokes. And you wonder how this happened. How could it be that even if still nowadays we don't have a complete understanding of the Cauchy problem for 3-dimensional Navier-Stokes equation, we are able to do quite well. Well, we do it thanks, to numerical simulations. And this is done first to the evolution of the computer. This is the first computer, the Pascaline by Blaise Pascal back in, in the 17th century. This was the ENIAC computer in the Second World War. Now this is a portable computer. And you know that with a portable computer, now you can do fantastic things that were impossible to be done, 60 years back during the Second World War with the most powerful computer, 80 years back. So you see how fast the evolution of scientific computing has been. This is why we can not only do fantastic applications in aeronautics, but also in hematology, right? In order to, advise doctors that are taking care, curing our cardiovascular system or cardiovascular surgery. This has the same mathematics, the same computational tools that are used for aeronautic optimal shape design can be used for hematology and cardiovascular health. Yet, if you ask me, I will tell you there is still an open problem. And all this is compatible. So as I have said before, the growth, the development of science is not linear, is not unidirectional, is done in a quite unstructured manner. And this is why there was a lot done in the computational direction that allows us to help cardiovascular medicine, yet we are not able to give a complete answer of the well-posedness of Navier-Stokes in 3 space dimensions. We know, thanks to the works of Jean Leray in the 30s, that in 2 space dimensions, Navier-Stokes is a well-posed Cauchy problem. In 3 dimensions, this is still an open problem.